Good morning. This is lecture 10 in Physical and Environmental Geography, GPY 100, and it is based on chapter 10, landform study. In this lecture, we are going to focus on the internal structure of the Earth. We will also identify the three rock classes of families and explain how they're formed. I would also talk and explain the classifications of igneous, sedimentary, and metamorphic rocks. And we would also explain the rock cycle and its significance. Finally, we are also going to talk about the importance of scale and processes in the study of geomorphology. Although the structure of the Earth is fairly well understood in general terms, there is still quite a lot that scientists don't know about what exactly is going on deep inside of our planet. Our humans have not penetrated more than just 1/1000th of the Earth's radius. So obviously we know much more what's going on in the Earth's crust and on the surface of our planet. And as we go deeper and deeper inside, all the knowledge that geologists have about what's going inside of the planet is really inferential knowledge of interior through either monitoring shock waves transmitted through Earth from earthquakes or from human-made explosions. So what do we know about the Earth's hot interior? Well, we know that temperature and pressure increase in general with depth, and the highest temperatures and pressure are at the center of the Earth. We also know that energy source is inside of the Earth is the radioactive decay of elements. Scientists have deduced that the Earth has a heavy inner core surrounded by three concentric layers of various composition and density. So we're going to take a look at each of these layers. These four regions are the crust, mantle, outer core, and inner core. The crust of the Earth is the outermost solid layer of Earth consisting of broad mixture of rock types. On average, crust is 3 times as thick under continents as under oceans, and the crust makes up less than just 1% of the volume of our planet. The next layer immediately underneath the crust is the mantle. This is the portion of the Earth beneath the crust, and it's surrounding the outer core about to depth of 2,900 kilometers, which is about 1,800 miles. The mantle has the largest volume of all four shells of the Earth, and it has three zones: the lithosphere, the asthenosphere, and mesosphere. The next major zone or shell inside of the Earth underneath the mantle is the outer core. This is the liquid or molten shell beneath the mantle, and it encloses the Earth's inner core. The outer core is responsible for generating Earth's magnetic field, which is switches in more or less cyclical fashion. And then finally, just in the very center of the Earth, there is the inner core, and this is actually believed to be solid, extremely dense, and this is innermost portion of our Earth. The crust of the Earth has very different depth and different thickness in different parts of the planet, and it's much deeper under the continents and much thinner under the oceans. And according to the theory of continental drift suggested by Alfred Wegener, the Earth's continents are actually continental plates that are moving all around the Earth. Alfred Wegener actually was not the first geologist who suggested this theory. He was the first to really formulate it as a viable hypothesis with evidence and specifically stated it as a theory, but many other geologists before him were coming up with very similar ideas. Building further on the theory of continental drift is the theory of plate tectonics. This is a comprehensive, coherent theory of massive crustal rearrangements based on the movement of continent-sized lithospheric plates that we see here on this map. The plate tectonics theory suggests that the Earth's outer mechanic layer, the lithosphere, is divided into large and smaller sized plates that are constantly moving in various directions. Some of them are moving away from each other, some of them are moving past each other, and some of them are moving towards each other, causing very different types of geological processes. And these plates are called tectonic plates. These massive tectonic plates are moving in various ways at different speed in different directions. And this has a huge impact on the Earth and the types of landforms that are being formed in different parts of the Earth along the plate tectonics boundaries. There are three main types of plate tectonic boundaries. The first one is convergent boundaries. This is where two plates are converging and colliding, and one plate is going underneath the other plate. When this is happening, subduction zones occur when one or both of the tectonic plates are actually composed of oceanic crust. So when I have the boundary, for example, of the oceanic crust and continental crust, and one crust is going underneath the other, this creates a subduction zone, and subduction zones are very much prone of earthquakes because of this convergence. There are also divergent boundaries. The divergent boundaries is where two plates are moving away from each other. And finally, there are also transform boundaries. Transform boundaries are happening when the plates slide past each other, and again, it can cause lots of commotion, and it can also cause earthquakes, such as, for example, in the San Andreas Fault in California. Now, the Earth crust is composed of minerals. A mineral is a naturally formed inorganic solid substance that has an unvarying chemical composition and characteristic crystal structure. There are about 4,400 minerals identified today, with new types of minerals still being found every year. In order for a substance to be considered a mineral, it must be solid, it should naturally be found in nature, it should be inorganic, possess a specific chemical composition, and contain atoms arranged in a regular pattern to form a solid substance. There are 7 principal categories of rock-forming minerals. Those are silicates, oxides, sulfides, sulfates, carbonates, halides, and native elements. The silicates is a category of mineral composed of silicon and oxygen combined with another element or elements. Oxides is a category of minerals composed of oxygen combined with another element. Sulfides is a category of mineral composed of sulfur combined with another element or elements. Sulfates is a category of minerals composed of sulfur and oxygen combined with another element or elements. Carbonates is a mineral that is a carbonate compound of calcium or magnesium. Halides is a category of minerals that are composed of salt, and they're salty. And finally, native elements are those minerals that are not combined chemicals with others, and are appearing as discrete elements, for example, gold or silver. Our lithosphere is composed of rocks. A rock is a solid material of aggregated mineral particles. Rocks are composed of minerals. A bedrock is a buried layer of residual rock which is not altered by erosion. A bedrock can be made of igneous, sedimentary, or metamorphic types of rocks and is often serving as a parent material for regolith or soils. An outcrop, as you can see here on this picture, is a surface exposure of a bedrock. There are 3 classes of rocks: igneous, sedimentary, and metamorphic, based on the processes that have formed them. Let's start by the igneous rocks. An igneous rock is a rock formed by solidification of molten magma. There are two types of igneous rocks that can be classified based on their mineral composition and texture: felsic igneous rocks and mafic igneous rocks. Felsic rocks contain large portion of light-colored silicate minerals. You can recognize them by much lighter colors. For example, granite can be pink or light gray. Mafic rocks contain low amount of silicates and they have much darker colors. Based on the way how rocks have been actually formed and their texture, there are plutonic and volcanic rocks. Plutonic or intrusive rocks are those igneous rocks that cool and solidify beneath Earth's surface. They usually have very large mineral crystals. Again, granite or diorite are good examples of those intrusive or plutonic rocks. You can clearly see them, they can be clearly identifiable because the crystals are large enough to be visible with naked eye. Volcanic or extrusive rocks, those are rocks that are ejected where the molten lava is ejected onto the surface of the earth and they solidify very quickly in the open air as they cool down. An example of such volcanic or extrusive rocks is basalt. Basalt is formed by flowing and quickly solidifying lava, and it has very small crystals. They're basically not invisible. Those grains are so small that we can only see them with an electronic microscope. The second major class of rocks are sedimentary rocks. Sedimentary rocks, as their name suggests, are formed of sediment that can be consolidated by a combination of pressure and cementation through a variety of different natural processes. There are three types of sedimentary rocks. Those are detrital, chemical, and organic. The detrital sedimentary rocks are composed of fragments of pre-existing rocks. For example, sandstone, as the name suggests, is composed of particles of sand. The chemical sedimentary rocks are chemically accumulated through precipitation of soluble material or through chemical reaction. An example of a chemical sedimentary rock would be a limestone. Finally, organic sedimentary rocks are accumulated organically from remains of dead plants or animals. For example, coal that we burn today as a fossil fuel is actually organic matter of dead animals and plants that lived millions of years ago. Petroleum and natural gas formation are also associated with accumulation of organic material in sedimentary deposits. So this is really ancient sunshine, right? Like all this energy that have been accumulated over millions and millions of years that has been staying in the ground for a very long time. And when we use it as fossil fuel, all these carbon emissions are going into the atmosphere. And this carbon has been accumulated over a very long period of time. So it's really not a good idea to burn it in a very short period of time and release all this carbon back into the atmosphere where it really has to stay under the ground. An example of the picture that I wanted to show you here is Epitosty stone, of course, the stone of the state stone of Michigan. And this is another example of organic sedimentary rock. Those are ancient corals that developed in the Great Lake region when it was under shallow tropical ocean. The third major class of rocks are the so-called metamorphic rocks. As the name metamorphic suggests, those are rocks that were originally something else and they have undergone metamorphosis, that means transformation. They used to be either igneous or sedimentary rocks and they have been drastically changed by massive forces of heat and pressure, usually both heat and pressure, sometimes just one of them, working on it from within the earth. So those previously igneous or sedimentary rocks that have undergone metamorphosis, and this could be contact metamorphosis or metamorphism when magma comes in contact with surrounding rock and changes it drastically, or it can be regional metamorphism when large volumes of rocks are subject to heat and pressure for a long period of time. This is common along boundaries of tectonic plates. There are two types of metamorphic rocks. Foliated metamorphic rocks, when there is a prominent alignment of orientation of minerals, as we can see here on this picture. There are low-grade metamorphic rocks, such as slate, medium-grade metamorphic rocks, such as schist, and high-grade metamorphic rocks, such as gneiss. There are also non-foliated metamorphic rocks, and this simply means that they don't have this foliated alignment of minerals. Its original rocks was dominated by a single mineral, and so foliation here is really not developing. There is a constant process of ongoing recycling of lithographic material via the rock cycle. So through the rock cycle, different types of rocks kind of recycled, moving from one class into another. For example, we know already that igneous rocks can be transformed into metamorphic rocks, but they can also be weathered and crushed and become very slowly sedimentary rocks. For example, igneous rocks such as basalt can over a long period of time become a sedimentary rock, first by becoming sand and then becoming a part of the sandstone. Sedimentary rocks, on the other hand, can then cemented and buried and under the influence of high temperature and pressure become metamorphic rocks. Metamorphic rocks can be melted under very high temperatures and then become again igneous rocks, and they can either erupt through volcanic eruptions and then become parts of lava, and this lava would solidify and would make again igneous extrusive rocks out of them, or this magma then can kind of infiltrate different hollow spaces and become extrusive rocks and crystallize and become also igneous rocks, more similar to basalt or diorite. So you can see that there is this constant recycling of different types of rocks as this material is moving between the crust and the lithosphere. As we know already, the lithosphere has very uneven distribution of sedimentary, igneous, and metamorphic rocks, and this is quite different from for the continental and ocean floor rocks. So you probably already remember that continental crust is much thicker than the ocean crust, but this is not the only difference. The continental crust is primarily made of silica and aluminum, and for short it's called Sial, while ocean crust is primarily made of silica and magnesium, and it's called for short SEMA. The isostasy is maintenance of the hydrostatic equilibrium of the Earth's crust. Where material is added, crust is going to sink, but it would rise when the material is removed, and so it's kind of maintain the crust in that constant relative equilibrium. It's important to realize that the landforms are developing at a very long geological scale. The geological time has a history of 4.6 billion years. And the history of the Earth is composed of four major eras: Precambrian, Paleozoic, Mesozoic, and Cainozoic. So we are living at the Cainozoic time. And this Cainozoic time consists of two periods, Tertiary and Quaternary. So we are living during Quaternary period. The Cainozoic era also consists of Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene epochs. And so we are living right now during the Holocene epoch. So, think about all this. It's a obviously very long geological scale, and many of geological processes are extremely slow. Finally, a few more terms and concepts that we need to know from Chapter 13 about the study of landforms. Topography is the surface configuration of Earth. Landform, an individual topographic feature. Geomorphology is the branch of physical geography and is the study of the characteristics, origin, and development of landforms. Relief is the difference in elevation between the highest and lowest points in an area, for example, vertical variation from mountaintop to a valley bottom. Internal processes that operate within the Earth, drawing energy from the heat, and external processes that operate at the base of atmosphere, drawing energy from sources above lithosphere from the sun. This concludes Chapter 13 and also GPY 100 Physical and Environmental Geography.